Okay, this is some old code. Last time also I said from the same code. This is the 5th lecture on forward kinematics. I'm just going to modify this. Let's start here and keep adding stuff till we get what we want. So let's call this planar Jacobian. And this is number 9. And then there were 2 things here. I don't want this, and I don't want this. We'll get rid of this extra folder. Okay, and I don't want this. I don't want just 2 files, but let me rename this as. Okay, okay, now all set. Let's go here and then open both of these files. Yeah, and then if I run this, it will basically give me the forward kinematics for some random configuration, some configuration. It just, for nonstop, it prints the position, and I don't want to do that. So let me just start off with this. Let me not run this for 100 seconds. Just 1 second is enough. And let's comment out the code which we are not interested in, which is all this stuff. So now when it runs, just runs briefly and then prints nothing. Yeah, it prints nothing. It's not printing. That's what we just wanted to print for an instant and go away. Okay, so now we are all set. Let's create a function called Jacobian end-effector. It's too long. Let's just call Jac end-effector. And then just like forward kinematics, we want to pass Q and param. So I actually need this. And if you remember, we do not need the angular velocity for this. We just need Q. Okay, so this has to return the Jacobian of the end effector. That's my goal. I'll call it pi j e. And then from import that. So we create a new file, Python, def. Inputs are those 2. And then return JE. Okay. And then the way I like to work on this is like, if I found it very hard to start from, it's sometimes easy to write the file the opposite direction of how it is written, which is I'm going to start from bottom and go work my way up, and you might find it an interesting way of working with code. So what I'm going to do is I'm going to try to create. I need to input basically. Where's that? Jacobian of E. Yeah, I need to input this stuff in there. Okay, so I'm going to compute the Jacobian of point E. So I think it's best to work backwards, because once I have these formulas down, I can then figure out what I need in order to get that working. So I'll work my way backwards in this code. So first, I will add JVE and then JWE. So JVE, if you look at the formula here, this is the easier. Let's look at the easier one. R00K, R10K, R20K. Zero K, R01K, R02K, 0K, E minus O00, E minus O10, and so on. Okay, so let me write that down. Cross with E0 minus O00, R01, K cross with 01. Okay, this is just helpful stuff. Now I don't need to refer to my notes. Okay, let's just get this going. So what I'm going to do is I'm going to use this thing called column stack. Stacks the column. So it has all this. Now this thing here is a cross product, but a cross product can be replaced with a skew. So what I'm going to do is I'm call this. I have it available in my utility file, vector skew. Okay, so I think this has to be the way I'm going to set this up. It's means I need to use ampersand at. Okay, then same thing here. Vector skew. Okay, let me just write a new line. It's going to be a lot of clutter here. So this actually helps you to continue a new line. Sometimes ignoring that is also fine. It's complaining here. I think it's because of this, or maybe because of NumPy. We'll take care of that later. Okay. Okay, this was the most time-consuming one, but it'll go much faster than this. And hopefully I'll end before the class, before we run out of time. Okay, that's that. This one is easy. JWE equals v dot column stack at K. Okay. Okay, then the JE is going to be another stack. Actually, np dot v stack JVE JWE. Okay, so it's complaining about lots of things here. It doesn't know R0. Let me just start defining those now. So import numpy as np. Import the one. I have to get this file. So luckily I've not. Let's call this jack and vector.py. Is it in the right place? Jacobian. I guess it's in the right place. Yeah, save. I just need to get that utility file and then we should be all good. Saved it somewhere here. Oh, there it is. Okay, so I have this, I have all this. Okay, now I need to actually get these values. So this is where I think I can use some of the work I did earlier. I already have this forward kinematics. Why don't I just call this and it will actually give me some things. Okay. So let's import from forward kinematics import forward. Okay, so I need to get all these things, and they are available here. Now let's see if I do send them. Turns out that I don't send all these things. So I need to send H01. I don't think I've computed H02 here. Okay, let's just compute it here, make my life easy. So H02 is H01, H12. And now it's easy to send this. H02 is H02, H03 was H03. I also need, okay, that's good enough. Let's go back to this and then pull it out. So sol equals forward kinematics cube. Okay, now we have H01 is sol dot H01. Three, two, two, three. I need R01, which is sol dot, no, it's H01, 3 rows, 3 columns. Then I just need to do 2 and 3. I don't think I need 3, but that should be there. Okay. So K is missing. K is np dot array 0, Z. Looks like I'm just going to run out of time. O equals H01, 3. O01, 2. Out of time. Okay, 0, 1, E0. Okay, E0, I think I have that. It's wrong place. It's saved as E. So E0 is sol dot E. R00 is missing. That's just identity. np dot I3. Okay, wow. Let's see if it runs. I doubt it'll run first time. Q is not defined. Let's fix that. Give me maybe 2 minutes more. I'll finish this. At least the first part, getting something to print. Then we can check it next time. Okay, what's missing is that it doesn't know what Q is. Let's Q equals data.qpose.copy. Could not do. Okay, this is, I know the problem is. This is a problem with E0, because if you see E0 in forward kinematics, I made it just 2 elements, needs 3. So let's fix this. Okay, printed. Let me just print it and then we'll stop, and then next time we'll do the verification. So I just said print y j e, print y j e. Okay, so it did print this. Okay, next. Okay, now I'm going to show you that you can do the same calculation. Well, MuJoCo does the same calculation, and you can get that from documentation. If you go here and search for Jack site. Okay, so Jack site is a function which gives you the Jacobian of a site, and why site? Because I put the end effector as a site in the XML. If you go back to the XML, so let me just use this. Right. I'm going to use this in the code here, in fact. Okay, so that function can be accessed by calling the package MJ, because I imported MuJoCo as MJ jack site. I need to pass in model. I need to pass in data. Jack P, Jack R, these are the linear and rotational parts. So the P and R is that. And then I need to give it the site index. So it's actually a site ID. Okay, so and you can actually figure this out. So this is actually some kind of a data structure, but here we have, when it says MJ denom, it's a special variable, which is a MuJoCo number, just like a double. They have defined their own set of variables. Here this is basically, think of it like a double, and then the site is actually an ID, it's a number. Okay, so how do we use this? Well, in order to call this way, we need to initialize Jack P, Jack R, otherwise it will not work. So let's initialize Jack P and Jack R. So the size of Jack P, it is going to be 3 cross n, where n is the degrees of freedom. So it's 3 cross 3. So I'm going to create Jack P as np dot zeros. And then I specifically want this to be a 3 cross 3 matrix within NumPy. So it's 3 cross 3. And note how this is done. There are 2 brackets. Okay, so same for Jack R, np dot zeros, 3 dot. Now you could also do it this way. I think model.nv, model dot. So within MuJoCo, it stores the number of number of degrees of freedom in NV. So 3 cross NV is what you want. And then site ID, this is basically something which you need to get. And the way you get it is if you search for, well, if you go to model MJ dot, no, sorry, model dot site, I need to see what it is called. So if you go to the XML file and scroll down, I've called it the tip, the site name. So I need to call it tip. And the way you get it is the ID. So this will actually be a number. So now site ID. So the variable Jack P and Jack R is what I'm interested. I'm going to just take those and then stack them together. So let's call this MJ, just like this. There's JE, so I'll call it JE. And what we'll do is do NP v stack Jack P, Jack R. Okay, and then final step is we'll print that and then see if they give you the same value. Okay, so everything works right, then we should have the same values for either of them. Okay, so this is the one obtained from Python. This is the one which we computed, and the one which we get from MuJoCo, and you can see that they're identical. Again, you can change it to a different pose and then get it. Now, there's another way you can do the same thing. This is just using a special function called jacksite. There's a more generic one available in MuJoCo, and I'll show you how to use that one. For that, you don't really need to. You can basically find the Jacobian of any point, and that point could be site, it could be the center of mass, it could be the body frame, and so on. I think it's called MJ Jack. MJ. Slightly different syntax, but we will use that. It'll be useful a little later. So let's take this. See how to use this. So this is method 1. Just put this. So this is method 1, and let's use a different method. Method 2. So let's just take this and then use this mj.mj check model data, same jack p jack r. Okay, so all those things remain the same. Check p check r, and then this one needs 2 more variables. Other one requires only 3. This one requires the constant mjtnum point and then int body. So I need to give the body name because that point could be on any body. So I need to find the where that site is. In fact, if you go here, you can see that the site is actually on the 3rd body. So site is in body equal to 3. So that's what I need for body. And so let me just get that. So here it will be, as you can see, it's an int. So again, I'll take body ID equals model dot body. I need the name. The name is body3. And then I need the ID. Okay, so I'm missing one argument, but the last one is body ID. Okay, and the finally is 0.3. What is 0.3? If you go back to the documentation, if you want to see what 0.3 is, I think it says okay, here it is. And a 3D point in world frame. So I need to give the position of whichever point I'm looking for in the world frame or in the global frame. Okay, so in this case, I'm looking at the position of the site in the world frame. So I first need to get the location of the site in the world frame. Turns out that we've done that before, right? How do you get the position of the site? There was another command, which I don't know if I still have it over here, maybe. Yeah, so do I have it here? No, I seem to have removed it. Oh, there it is. So this is how you get the position of the site, right? It's taken from the forward kinematics one. So this is data site tip exposes the X, Y, Z location in the world frame. All I need is take this, put it here, and I will comment out this because right, I'm not, well, I need this though. Okay, so this was how I get jack p jack r. This was the first method. Let's see if this is producing the same results as the other one. So you stop. Okay, so you can see, compare the two, you get the same answer. So all the 3 are giving the same answer: jack, site, MJ jack, and as well as what we did. Okay, now the reason is why are we actually doing these calculations and MuJoCo is actually giving the values? Now, MuJoCo is a special simulator. It's one which is more friendly to do these calculations such as Jacobians and use them for your work. Many simulators out there don't give you Jacobians. They will only do, you can only supply things like torques or forces, and then they'll do something for you, but they will not really give you the Jacobian. So it's good to know how to compute the Jacobian because you can't assume that the simulator will give you. The other place where uh, you could use the Jacobians, your calculations, is because sometimes it does happen that you cannot run MuJoCo on the robot for whatever reasons. Maybe it requires too much computation, too much the graphics or the CPU needs are much higher than what your hardware can provide. So in that case, you're better off writing your own calculations in the back end so you can use them for your online calculations. Sometimes you just have to optimize things. So things like that are important. Maybe MuJoCo Python is slow for you. So many things. So it's always good to know how to do these things. And that's why what we're trying to do in this course is we are looking at what MuJoCo provides as a way to check our calculations, but we're doing all the calculations ourselves. Okay, so that's that. Now, this basically gave us a way to verify the Jacobian of the site. The other calculation we did last class was, I think we also, well, for the same three-link manipulator, we were trying to compute the torque needed at each joint. And that torque, it turns out that is related to the Jacobian. If you know the Jacobian, in fact, the linear part Jacobian, and you multiply with the force, which is the gravitational force, you get the torque. This is basically saying that you don't really need to draw free body diagrams. You can actually use this. So you've learned free body diagrams probably in an undergraduate statics class, okay, which is a big deal, but you can't do it without that if you know how to compute the Jacobian. So what I did was I essentially went to this example and I wrote down Jacobian for V using a similar approach as I used previously for the site. I've only computed Jacobian of the linear part. So what I'm going to do next is show you how you can transfer these calculations to MuJoCo. In fact, I will not really compute the torque. Okay, I just compute the Jacobians. I'll compute both the Jacobians, the linear as well as the rotational Jacobian, and then I will compare that against the Jacobian which you got from Jacobian you got from MuJoCo. Okay, and we can use the similar things. Let's see. So here's what I'll do is similar to this one. I'll create another file. I think I can use a lot of things, reuse a lot of things, but I just want to keep my calculations in a separate file so that way it's easier for you to refer to this. So let's call it JackCom, save. We'll rename this file, this function as JackCom. Let's just go ahead and start putting this together. Okay, you can use a lot of things from this file. What I'll do is just think maybe a shorter, instead of doing it for every single link, let me just do one of the three, okay, instead of doing all of them. And I can maybe provide the code later on, just to, in the interest of time, let me just compute the Jacobian of VG2 and J omega G2, and then check against MuJoCo. But then when I post it, I'll finish the code and give you all the values. You'll need this later on. So let's do verification for JVG2. That's it. And then see how it compares against MuJoCo. So for that, what we need to do is we'll just write the formula just like this: JVG2. This will be G2, G2, G2. I think that one means the same. Okay, so here G2, I wrote it as it is. There'll be a 0 here. There'll be actually 3 zeros, 3 cross 1, and everything else remains the same. So let's go here, and this is all fine. This will be zeros, 3 cross 1. G2, G2, and this will be np dot zeros 3 1. Okay, I have not yet defined G2. We'll do that. Here we'll, if you, now this I have not written on my notes, but it will have a similar flavor as JVG2. This will just be np dot zeros 3, 1. G2. Okay. Okay, what remains is only to find what G2 is. G2 is the position of the center of mass of the second link. This is G2. So what I need to do is I need to get H02 and then multiply it with the position of G2 in the local frame, which is 0.5 L2. It's half of L2, right? It's half midway along x-axis and then 0 along the y, 0 along the z. So let's do that. So G2 is H03, 3, no, it's H, my bad, times np dot array 0.5 times L2, 0, 0, and 1. This is just a homogeneous part. And then for G2, I need to get rid of the fourth column because the fourth column is 1. So one way of doing that is to say 3, 0, 1, 2. Yeah. Now L2 is not defined. Okay. So can find L2 in the params. If you look at forward kinematics, so if you look at forward kinematics, this is how L2 is defined. So let's just pull that up. Okay, so now L2 is defined. And then that should hopefully work. Okay, so I'll just import this function, and then we should be all set to go. So from jaccom import jaccom. So first thing, and then go here, and I don't want, let me just comment the other word. Okay, the easier way to comment, I like to do this, which is just put an if statement. If it's 0, it will not print. Oh no. Okay. So I'm going to call J2 equals jaccom, and the inputs to that are going to be Q and I think params. And then let's just call that pi jg2, and then print pi j g2 okay. So let's see if this works. Okay, so this is it's going to, why did it print JE? Okay, I shouldn't have printed this part. Oh, it's outside, I think. Oh, I see. Let's get rid of this. Just move in that if loop, so I don't have to. Okay, now let's run this, and I will only print what I need it to print, which is pi jg2. Okay, now I need to verify this is actually what it is from MuJoCo. So what I can do here is the following. Again, there are two ways to get this. One is use the generic MJJack, which, as I said, works for anything. But here we'll do it using another specialized command. It's called, I think, jack com or jack underscore c. Oh, maybe it's co caps. Maybe it's like this. No, we'll search it near mj jack body maybe. Let's see what this does. Jack body com. Compute body of center of mass end-effector. End-effector Jacobian. I think it's jack body, not jack body com. Let me quickly check this. Don't remember the top of my head. Yeah, it's jack body com. So jack body com is going to be the center of mass. I need to take this. I can also, I think, copy this. Let's see. Okay. Okay, let's start getting this mj jack body com model data, easier part, jack p jack r as usual, jack r. Then I need to give the body, that's it. So which is that body? It's actually an int. So it's going to be, if I'm not mistaken, body 2. We're interested in body 2. So I'll use a similar, let's call this body ID. And then for body ID, I get it the same way as before, which is model dot body, the name of the body, body 2, and then I need its ID. Okay, so just print this. Oh, so I need to stack them. You can copy paste this code. So we'll just take all this. Let's call this G2, G2, G2. Okay, here is oh, they're different. Made some error. Okay, I need to debug this. So we don't have the same value. Seems like the Jacobian V is wrong. I suspect it's to do with G2. No, for sure these are right. So G2 might be wrong. Oh yes, this is wrong. H02, right? Because it's the second body. Okay. Yeah, they agree. Here it is. Same thing. From this you can you can find JG1 and JG3. Okay, but this just shows that how you can do verification.